Assalamu alaikum. This morning I'm quite happy because we're going to finish off Maxwell's equations. We're going to complete the set that we started off a couple of months ago. However, before I go on to that, I would like to talk about a few nuances, few subtleties about motional EMF. This question has been inspired by some students inside the class. We've already seen that if I have a loop of wire that is placed inside a magnetic field, and suppose that magnetic field is pointing out of the plane of the paper, it's a uniform field, which means it's the same everywhere. It does not depend upon position. No EMF is generated inside this loop. There's nothing moving. Now, if this field is time varying, for example, if this field goes up, outwards, it's increasing in the outward direction with time, an EMF will be generated. Remember that this loop is static. The EMF that is generated, E, which will be an integral of the electric field that is developed inside this closed path over the path, E dot with dl. This is the closed path we're talking about. This will be given by the negative of the derivative of the flux that passes through this area, and that is the area which is on the inner surface of this loop. So this is a loop, and the area that is bounded by the loop, you find flux through it and find the time derivative of it. That gives you the EMF. And this electric field that is developed inside this loop has nothing to do with charges. It only has to do with the changing magnetic field, and nothing is moving here, by the way. Right? So this electric field that's developed here is non-conservative. And there are no charges associated with the EMF. However, when a current flows because of this EMF, and if this loop of wire has some resistance R, then in order to make the current bend on these edges, slight charges will be developed here. But that's it. There's no surface charge gradient on this straight section. The entire current is being produced by an EMF that has been made up by a changing magnetic flux, and there's nothing moving in this scenario. Okay, we all know this. However, we've also seen cases in which the magnetic field is uniform and it's not changing with time, but we have a conductor that's moving inside this configuration, for example, and that is what we call motional EMF. Now suppose that we have a conductor, a conducting rod for example, that is moving towards the right with the speed v inside this uniform magnetic field. And it's not only a uniform field, it's a static field as well. It's not changing with time. And this is connected to a fixed circuit. Everything else is rigid, but this conductor is moving. So as this conductor moves, it stretches these wires, or you could consider that this conductor is moving on frictionless rails. Now we've seen that a motional EMF is developed, and in this case that EMF is also given by this relationship, minus d by dt v dot will be dA. However, now we have motion of a circuit, a motion of a piece of wire. Therefore, we've also seen that the electric field that is developed inside this rod is due to a magnetic force acting on the electrons. So if the electrons are moving towards the left, the field is pointing out, the force is pointing upward on the electrons. So this rod becomes polarized. A positive charge develops here and a negative charge develops here. These are real charges. So the electric field is set up inside this wire, inside this rod, this is the direction of the electric field inside the rod. But outside the electric rod, inside the fixed circuit, this is what the direction of the electric field is. And this is just like a battery. And the charge gradients are developed on this circuit. So this charge will dilute itself as we go around the circuit. And this charge dilution will cause a current to flow. Now this is a conservative electric field. And since it's a conservative electric field, we have E dotted with dl around this closed path P. This is my path P, is 0 in this case. But in this case as well, similar to what we have written here, the EMF is indeed equal to the time derivative of the flux through this circuit. However, E dot dl about this closed path is equal to 0. It's not equal to the EMF. It's only that the motional EMF that is developed across this conductor alone is equal to the time rate, the rate of change of the flux through the entire circuit. That's the EMF that's developed inside this rod. So this is true. This is always true, whether the rod is moving or it's static. However, E dot dl in this case is 0 because the electric field that's developed inside the circuit is all conservative. Okay? So this relationship, this general relationship, E dot with dl equals minus the time derivative of the flux through a circuit has to be taken with a pinch of salt. It applies to static conductors. When we have moving conductors inside magnetic fields, or we have a static conductor and we have a magnetic field that is swept across, spatially swept across the conductor, then we have to take into account relativistic effects. And this is something that I'm going to deal with later. But in any case, whenever you have a moving conductor inside a magnetic field or you have a changing magnetic field, an EMF is developed inside that circuit, and that EMF is given by the time derivative of the flux through a closed circuit. Now let's look at another example, quite an interesting example, and that is of a homopolar generator. Now suppose it's quite an interesting scenario that I would like to talk about. Suppose this is a uniform magnetic field and it's static. So it's static and it's uniform. And I have a piece of wire, a square-shaped piece of wire, conducting wire, and it's moving with a velocity v, a uniform speed v inside this uniform magnetic field. Will an EMF be induced inside this field, inside this wire? The field is static, it's uniform, it's unchanging, and I have a rigid piece of wire and it's swept through the field. Will an EMF be induced inside this wire? No, because there's no change in flux that pierces the area. The EMF induced is 0. Alright? Is that true, Smanuni? The flux is pointing out, the magnetic field is pointing out, but when it's moving, this is the path, the loop. What's the flux through the area? So the area is pointing outwards, the flux is pointing outwards. So, right, so there is some flux that is cutting through the loop, but is that flux changing with time? Smile. The flux is not changing with time. No doubt there is flux piercing this area, but the flux is not changing with time. So an EMF will not be induced inside this circuit, and no current will flow through this circuit. Suppose I just have a single piece of rod. Will an EMF be induced inside this rod? This is moving with a speed v. Now what I'm going to do, I'm going to dissolve this object into 4 pieces. A top piece, a bottom piece, right piece, left piece. If I just look at this piece in isolation, is an EMF going to be induced inside this? Is there a motional EMF? Is there a magnetic force that acts on the electrons? Yes, there is a motional EMF that is produced. So an electron is moving to the right. So the field on an electron is in the upward direction. So electrons will accumulate on this top surface. And when electrons accumulate on this top surface, there will be a depletion of electrons here. So this top surface is acquiring a negative charge, and this bottom periphery of the top segment is acquiring a positive charge. Likewise, here you will develop a positive charge, and here you're going to develop a negative charge. Now this wire on its own can get polarized, but there is no gradient of charge across this surface. There is no gradient of charge across this surface. No current can flow. And what this scenario is, actually this scenario, you can draw an equivalent circuit to this scenario. So, alright, I'm so sorry. So this situation is exactly analogous to the situation above. This negative charge here and this positive charge here. Okay, it's exactly analogous to this. So an electron is moving to the right. The force on the electron is in the upward direction. So in this section, electrons will be shifted slightly upward, and there will be depletion of electrons here. So this becomes positive, this becomes negative. Alright. Now, likewise on this surface, this end will also get polarized slightly, will it? So if this rod is moving, if you consider this piece of wire in its entirety, if this piece is moving towards the right, the electrons will be shifted in the upward direction, so electrons will accumulate here, and there will be a positive charge that develops here. But this configuration of charges, which is developed as a result of magnetic forces on the electrons inside this wire, cannot make a current go around the circuit. It will not create an EMF. Alright? There's no way an EMF can develop inside this loop. If you would like to draw an equivalent circuit of this is similar to the configuration that we have here. I mean, there is no way an EMF can develop. This configuration of charges cannot create a current through this closed loop. Alright, now let's consider an alternative scenario, which is quite interesting in its own right. And that is called a homopolar generator. That's what I'm going to talk about. Suppose I have a metallic disc, a circular disc of some radius r. So it's a disc, and this disc is rotating with the speed omega. And angular speed omega. And what I have is, I have a carbon brush here and a carbon brush here. And I extend wires out of these carbon brushes. So what happens is that this metallic disc is rotating with a certain speed omega, and it is just skimming the brushes. It's just barely touching the brushes. And all of these are conductors. So these brushes are static, these wires are static, but this disc is spinning at frequency omega. When this disc spins at the frequency omega, it skims these contacts. It makes electrical connection with these contacts, and then I have a resistor here, R. Now my question to you is that this field is static and it's uniform. Will an EMF be induced inside this circuit which will cause a current to flow through the circuit? Just think about this. I give you a couple of minutes to think about this. Will an EMF be induced inside this circuit? In other words, will a current flow through this circuit? And what's the direction of that current? B is uniform here. Just to finish this off, suppose we have this top conductor and we have a bottom conductor. This bottom conductor also develops a charge, positive charge here, a negative charge here. Suppose these conductors are just connected by thin, infinitesimally thin wires. So I do have a closed path, but then I have these conductors at the top and the bottom which develop charge distributions like this. Now the potential of this end is zero because it's neutral. The potential of this end is zero because it's neutral, and no current can flow inside this circuit because both of these are at the same potential, and that's why an EMF will not be induced. So this is just to formalize the argument that we were talking about previously. Now, will an EMF be induced inside the circuit, and will a current flow? Akif. There will be an EMF induced, and will a current flow? A current will flow. Is it possible for you to predict the direction of this current? Now let's break up this disk into rods so that we simplify our problem. This is called the process of dissolving a problem into smaller problems. So instead of a big disk, suppose I have a rotating disk inside a uniform field. So instead of this disk, let's draw a rod. So I have a rod. One end of this rod is fixed, and this is immersed in a uniform static magnetic field. This rod is moving with the speed omega. Okay, and now I constitute a circuit R. Okay. Now the difference between these configurations is twofold. First, here I have a disc, but here I have a rotating rod which is pinned here. It has its axle here, so it's immovable from this position, and this end is rotating with the frequency omega. So with time, what's going to happen is that this end is going to shift its position, and this end of the wire is going to stretch. So what I would like to do is, I would like to draw this rod at a different position, at a later position. At some later position, this is what the rod is going to look like. And I have a uniform magnetic field, which is on all the time, and it's not changing with position. So if omega is the frequency of this rod is going to stretch the circuit. Now what I would like to consider is the following. If this angle is theta, at some time t naught, this is the angle at some later time, t naught plus delta t. Now, is the flux through the circuit changing with time? G. No, the angle is not changing. The magnetic field is outward and the area vector is always outward. So the angle between the magnetic field and the area vector is not changing. However, the area itself is changing, because as this rod traverses an angular path, the area of this circuit changes. So there is a change in the area, and hence a change in the flux that threads this circuit. Since there is a change in the flux, an EMF will be induced. Do you understand this point? Since I'm stretching this circuit, this rod is going round and round and around. The area of this circuit, which is seeing a magnetic field, and hence the flux through this area is changing with time, simply because this angle is changing with time. But the angle between the magnetic field and the area vector is not changing. Both of them are pointing out of the plane of the blackboard. So the area itself is changing, and EMF will indeed be induced. Now, if I would like to look at the direction of the EMF, this is an example of a motional EMF. Consider an electron here. At some point, this is the direction of its velocity. Will there be a magnetic force on the electrons? Yes. What's the direction of that force? So this is V, magnetic field is upward, so the force is pointing downwards. So these electrons will tend to accumulate here, and there will be a depletion of electrons here. So an internal electric field will be set up inside the rod, and an EMF will be set up inside, an electric field will be set up inside these wires, which will cause a current to flow. And the EMF that is set up inside this rod is simply going to be given by Faraday's law, minus the time rate of the magnetic flux that pierces this circuit. Alright? Now if I would like to find out this rate of change of flux, how would I go about doing this? Now this situation is totally different from this situation, because in this situation the circuit is fixed because we have carbon brushes here. The circuit is not rotating. This end of the wire is not changing its position with time. So this circuit is evidently different from this circuit, or at least apparently different from this circuit. Alright, so there's a marked difference between what I've drawn here and what this homopolar generator is. Because in the homopolar generator, this point is fixed. Here, this point is changing. It's extending with time because this rod is moving. Now if I were to calculate the area which this circuit which this flux sees, how would I calculate that area? What I would do, I would just draw a circle here. So this rod is now moving on the circumference of the circle. Okay? So the flux is changing. There is some constant area here. Okay? This area is constant. I call this area A dash. Can you tell me what the area will be as a function of time? This is the area through which the flux is piercing, through which the magnetic field is passing. What is this area as a function of time? It's A dash plus half r squared into omega. How do you get this? Exactly. You get this by theta over 2 pi into pi r squared. Okay? It's half r squared over 2. Theta is simply omega t. So this is the area as a function of time. Now the flux through this entire circuit, B dotted with A as a function of time, B into dA as a function of time integrated over this entire loop. Now B is constant, so I can take this out of the integral. The angle between, if I break this circuit into small sections, this area into small sections, the area vector is always pointing outwards, and so is the field. So the angle between B and the infinitesimal area element is 0. So cosine theta is 1. So I can take B out of the integral. dA comes here. This is a function of time, by the way. Alright. This will give me the area as a function of time. Now this total area is given by this. So I have B into A dash plus half r square omega t. This is the flux through the circuit as a function of time. And in time, it depends upon time. Now I would like to take the time derivative of this. In the time derivative, A dash is immaterial because it's constant. So it doesn't matter. So the time derivative of this will give me the EMF. The EMF induced will be equal to minus B, R squared is fixed, omega is fixed too. This is the EMF induced inside this rod. So the EMF induced inside this rod will cause a current to flow through the circuit. And the current that flows through the circuit is simply this EMF divided by this resistor R. Now notice something quite interesting here. I have a rod that is circumambulating a circle, it's moving around in a circle. And I have a piece of wire that is pinned to this edge of the rod. And there's a current that starts flowing through the circuit. This current can deliver power to the resistor. This rod that is rotating inside a uniform magnetic field is acting like a generator. It's acting like a battery. There is an EMF induced inside the rod which causes a current to flow through the circuit. And it's a conservative electric field all throughout the circuit. And this EMF is a constant because omega is a constant, everything else here is a constant. A constant current is going to flow through the circuit. But this is not a practical way of generating an EMF because as this wire rotates, it's difficult to make this wire stretchable. This really has to be an elastic piece of copper. So what you would like to actually have is you would like to have this end of the wire fixed, and instead of a rod you have a complete disc. Remember that this EMF is only depending upon the angular speed. So instead of having a piece of rod. You have a complete disk. And what a complete disk means is that it is comprised of many rods. One rod is moving in this direction. It skims or skirts this piece of wire, it touches this piece of wire and a current flows. Then when this piece of rod has gone beyond this point, another piece of rod is rushing inwards and it's going to touch this piece of wire. So one rod after the other is going to come and brush this piece of wire and it's going to create an EMF which will cause a current to flow. So this homopolar generator will create an EMF that is exactly equal to the EMF that we calculated here. Ji sir.
So the area is not changing in that case because another rod will take its place, so the area will be flux both the.
Okay, I'm going to answer this question, but do you understand my argument? My argument is that I'm breaking up this case into the following case. I have a static piece of wire, a resistor, and then I have multiple rods. So I have one rod, one piece of rod that comes and touches this piece of wire and it moves forward. Then the connection of this piece of rod with the wire breaks. Then I have another piece of rod, another section of the circular disc that comes and touches this piece of wire. And it's happening continuously. And each rod has an EMF induced in it. And that EMF is the motional EMF that we calculated here. And that EMF is available to deliver current to the resistor. And hence it can cause a light bulb to glow. So this is what is happening here. So this circuit is exactly equivalent to this circuit. In this circuit, the flux is changing. So if an EMF is induced here, an EMF is also going to be induced here. Okay. And if I would like to draw an equivalent circuit here, it's just a battery of EMF E, which is given by minus, or in this case, the magnitude of this EMF is B R square omega over 2, and this is connected to a resistor R. So such a kind of a generator is called a homopolar generator. And notice something quite interesting. It creates a direct current, a DC current. Even though we have a rotating disc, yet it produces a current that is unidirectional. It doesn't change with time. Its direction remains fixed. So it's a DC source. It's an example not of an alternator which produces an AC, it produces a DC, even though we have a rotating disc. Now, what if I have this rotating disc and instead of tapping off the connections at this point, I tap off the connections on diametrically opposite points of this rotating disc? What's going to happen in this case? Will an EMF be generated? And will a current flow through this resistor? बिलाल क्या ख्याल है? नहीं होगा. क्यों नहीं होगा? The EMS will be in the opposite directions. Now I can dissolve this disc into two rods that are rotating in the same direction. I look at the top rod here. This rod is moving in this direction, so the velocity of the electrons at some instant is this. And there will be a motional EMF. So if the electron is moving here, the field is pointing out, the force on the electron is in the downward direction. So electrons will accumulate here, and there will be a depletion of electrons here. If this wire was here at the center of this disc, so then indeed an EMF will be induced which will cause a current. But now let's look at the other half diameter of this disc, that is another rod here. Now the electron has a velocity that's pointing in this direction. Remember once again, the electric field is pointing out of the plane of the black hole. Now consider the force on an electron. The force is in the upward direction. So this motion will also create electrons here, and it will create positive charges here. So all along this diameter, now you join these things together, you glue them together. Conceptually, what's going to happen is there's going to be a gradient of charge on the surface of this disk. The outer periphery of this disk is going to be positively charged. The entire outer periphery is going to be positively charged, and as you move inwards, at the center of the disk there will be a preponderance or a majority of negative charges. So here there will be a negative charge, here there will be a positive charge. Now you have a moving disk inside an electric field, its surface becomes polarized. There's a distribution of charges, and in between the charge at half the radius, at these locations there will be zero charge. So there's going to be a gradient of charge, and that's going to remain fixed. Now this is a conservative electric field. However, it will not create an EMF, because if this is where you're tapping off the voltages from, this potential is at the same potential as at this point. So there's no potential difference between these points, and it cannot cause a current to flow through this resistor. So this configuration, even though it has generated charges on the surface, you're not utilizing the charge distribution. You can, if you would like to, you just pick up this piece of wire and put it here. You will create a DC through this resistor. But in this case, no doubt an EMF is going to be produced inside this disk, but you're not tapping or you're not utilizing this EMF. Okay? If you would like to draw the equivalent circuit for this, this is a battery, and this is another battery. But the two batteries are connected in this fashion. So the two batteries are connected in this fashion, which means that the net EMF across these terminals is zero. These batteries have been connected in opposition to one another. Since they have been connected in opposition to one another, they cannot cause a current to flow through this resistor. Because if you would like a current to flow, you would really need a charge gradient here. Here, you see you have negative charges here, you have the same amount of negative charge. No electric field is established here, so no current can flow through this circuit. Okay? Here you have a positive charge. You have the same positive charge here. No gradient can be established because of symmetry inside this piece of wire. Hence, there is no charge gradient, no current can flow. Remember, currents only flow because of charge gradients on surfaces. Now, all of these nuances and subtleties have to do with motional EMF. So once you get the hang of Faraday's law, that an induced EMF is given by the rate of change of flux, a conservative or a non-conservative electric field is produced that can drive a current through a circuit, through a resistor. It can deliver power to the resistor. Once you get the hang of it, you get the feel of it, you can look at problems of all kinds. But you really need to work hard. You really need to spend some time with this material. Unless you spend time with this material, it's really hard to grasp what's going on. Now, there was another question asked by students. I'm always adaptable to changing the course of my discussions based upon student questions. The second question I would like to talk about is about superconductors. And I've already dealt with superconductors in some detail, but a quick overview before we move on to the final Maxwell's equation. Suppose I have a superconducting ring of radius r. This ring is kept at temperatures above the critical point. So it's non-superconducting at these temperatures. Okay. Now I have a magnet placed close to it, North Pole here, and a flux phi naught threads this superconducting coil. So the flux through this coil is phi naught, and the direction of that flux is this. Okay? And I suppose that capital R is really small. So I ignored the variation of the magnetic field inside the loop. So it's made of a superconducting material, but it has not yet been driven into the superconducting stage because the temperature is high. Alright? Now what I would like to do. This is step 1. In the second step, I have this magnet in position, nothing changes. I have the superconducting loop, and I place this inside a thermos in which there is liquid nitrogen. Like this is a kind of superconductor I showed you in the class. Now the temperature is below the critical point. So now it's superconducting. Still a flux phi naught threads this superconductor because the position of this magnet hasn't changed. Will a current flow through the superconducting coil in this case? Akila? The current will not flow. There is no current flowing in this piece of wire, and there is no current flowing through this piece of wire. Nothing has changed. And the flux through this piece of wire is still phi naught, so nothing has changed. Now the next step, what I would like to do, I would like to remove this magnet. Okay, quite an interesting experiment. So in the third case, I remove this magnet. So still I have the superconducting coil placed inside a dewar of liquid nitrogen. Now what's going to happen? The flux through this coil in this scenario was phi naught. Now what's going to happen to the flux? As I told you, the superconductor is a flux change opposer. It does not like changes in flux. Why? I'll tell you in a minute, but it does not like changes in flux. So it would still like to have that flux phi naught, which was created by some other source. Still it would like that flux to persist through it, even though the source has gone away. Right? It's become used to or habituated to this flux. It does not like change in flux. So it would still like that flux to pass through it, but the magnet isn't there. So this flux has to exist. So how can that flux exist? By a current. A current is produced out of the blue, out of nowhere, inside the superconducting coil, which will cause a flux through this piece of wire. Now what's the direction of that current? It's going to come out of the plane of the blackboard at the top and into at the bottom. And this amount of current is just the right amount to produce a flux phi naught. We've calculated this amount of current. And it's going to be a finite current. You can calculate what this current is. If this area is pi r squared, b pi r squared, this is phi naught. You would like to create a B at this point which creates this flux. How is a B created? You use the Biot-Savart law. B is created by mu naught. I is the finite current, is the current to the superconductor, mu naught over 4 pi dl cross r, dl cross r, alright, so this is 2 pi r squared. This is the Biot-Savart law. So you use this magnetic field, put it in here, you know what the flux needed is, you can calculate what the finite current that is flowing through the solenoid is going to be. This comes out from Biot-Savart law. You just find the magnetic field at the center of a current carrying loop. We've already done that. So this amount of current flows through this superconducting ring out of nowhere. The magnet has just gone away. So you have a magnet, you place it near a piece of wire which is superconducting at certain temperatures, you remove the magnet and a current starts to flow through the superconducting coil. And this current will persist forever up till probably the day of judgment. If this object is placed inside liquid nitrogen and you don't let this nitrogen to vaporize, because this nitrogen is going to vaporize with time, if you keep this object cool enough, you can create a current. And this current will not cause any power losses because it's a superconductor. There is no resistance. So this is a persistent current. It's going to persist forever. Now this current I finite, generally we say that I finite is given by some EMF divided by resistance. So the resistance in this case, this has to be finite. There is no such thing as an infinite current. This is a finite current, but the resistance is zero. So the only possibility is that this EMF that's induced inside the superconductor is zero. So in a superconductor, there is no electric field set up inside the piece of wire. Still it can carry a current. So physics is beautiful at its extreme. In normal conductors, you have an electric field inside the conductor which causes the current to flow. In a superconductor, you can have current flowing without voltage drop, without EMFs, without electric fields. जी यार
सर यहाँ पे ठीक है मैग्नेटिक फील्ड भी करंट से प्रोड्यूस होगी ना
हाँ जी
तो अगर उस मैग्नेटिक फील्ड में हमें करंट कैरी वायर रखते हैं तो उसके ऊपर जो फोर्स होगी वो क्या कॉन्स्टेंटली प्रेजेंट रहेगी फिर
कॉन्स्टेंटली प्रेजेंट रहेगी
तो वो फोर्स की एनर्जी कहाँ से आएगी कांस्टेंट फोर्स तो नहीं हो सकती ना
It will cause induced currents in the super.
इसका टेम्परेचर देखो एंट्रोपी देखो इसकी it's coming from entropy. Okay? So here thermodynamics has a major role to play because the temperature of this superconducting coil is really small. You have used energy in order to liquefy nitrogen. It's a temperature that's playing a role here. Okay, by the way, the magnetic field can never do any work. Okay? Alright, now what I would like to talk about is one other point. The EMF induced inside the circuit has to be zero. Inside this piece of wire. I also gave you the example of, another example I talked about is, why is the superconductor flux change opposite? Remember that the EMF inside the superconductor is zero. It has to be zero. Because if this is non-zero, you will have some E dotted with dl non-zero inside the superconductor. And you multiply this with a charge on a charge carrier inside the superconductor, which can be a Cooper pair. So I'm not putting the charge on an electron here. It's some Q here, which is carrying charge inside the superconductor. Remember, it's not an electron. It's some other species. Some Cooper pair, some pair of electrons. If this is non-zero, it will cause a change in energy. But there's no change in energy when when a charge carrier goes around a complete loop inside a superconductor, because otherwise it will dissipate energy, and that's not allowed. So the EMF induced inside a superconductor is zero. But we also know that the EMF is given by minus d phi by dt. If this is zero, it means that the flux has to be constant. That's why the superconductor is a flux change opposite. It likes to keep the flux to it constant. And we also looked at the example of Meissner effect. In the Meissner effect, instead of having a superconducting coil, we had a superconducting disk. So not only are the electrical properties of superconductors quite interesting, but also the magnetic properties. A superconductor is different from a perfect conductor. It's beyond that. A perfect conductor has infinite conductivity or zero resistivity, but a superconductor goes beyond that. It has interesting magnetic properties as well. And the magnetic property that interests or excites us is that its susceptibility is -1. It's a perfect diamagnet. That's why the field inside has to be zero. Alright? So when I place this close to a big magnet here, and this superconductor is below its critical temperature, it levitates. The superconductor levitates. If this magnet is fixed, the superconductor levitates. If this superconductor is fixed, the magnet will levitate. Now why is that? Because you would like to keep the field inside 0. Now this magnet is producing its own magnetic field, H. But you would like to create a magnetization inside the superconductor that's almost, it's not almost, it's perfectly equal and opposite to H. So that you have a net field B inside 0. So in response to this H, you produce a magnetization M, which is equal and opposite to H. So the net field inside is 0. And how is this M produced? I told you about it. It's produced by currents only on the surface of the superconductor. Okay? So in this case, if you would like to produce a magnetization, there will be currents flowing on the outer periphery of the superconductor. So if I look at the superconductor from the top, a magnetization is going to be produced that's pointing into the plane of the blackboard, which means that currents are going around like this, only on the surface. These are surface currents, i.e. surface. They are also called screening currents because they screen the magnetic field from penetrating inside this superconductor. And why only on the surface? This was one of your questions. Simply because of Ampere's law. Because Ampere's law tells us that B dot will be dl about the closed path is mu naught I. The current that pierces this closed path. If B is 0 everywhere, I has to be 0 inside. Since there is no magnetic field inside, it's identically 0 everywhere. Therefore, there can exist no current inside this bulk material. Therefore, any currents that exist on superconductors, they must lie on the outer periphery. This is a special kind of superconductor, by the way, which is called a type 1 superconductor. Just out of curiosity, out of technological interest, I would like to mention that there are certain superconductors called type 2 superconductors, in which the flux can penetrate the bulk, but only in small regions. So flux is only coming out through these small regions. So if I draw a diagram of the superconductor placed inside a magnetic field H, the flux is going to come out through these small regions, and it's not going to penetrate the entire bulk of the superconductor. It's going to be threaded into these small holes inside the superconductor. These holes are called vortices. This is a kind of superconductor which is called a type 2 superconductor. Anyway, the superconductor that we dealt with in the classroom is a type 2 superconductor. I would like to take a half minute of silence before we conclude our discussion of Maxwell's equations. see what happens when magnetic fields change, or when magnetic fluxes change, or when conductors move inside uniform magnetic fields. Now let's see what happens if electric fields change. I have a piece of wire, a long thin piece of wire that carries a current, a uniform steady current I. It's not necessarily steady, it can depend upon time, but it's uniform. Now instead of having a continuous wire, I have a metal disc here, which is the plate of a capacitor. And then I have a neighboring plate of a capacitor. Two identical plates here. And then I have this piece of wire that is continuing on the other side of this capacitor. And the current that flows through this entire circuit, I, is a function of time. Now the first question is, how does current go about this capacitor? This is an insulator. And this electric current, which will create a deposition of charges on these plates, does not produce a strong enough potential difference so that the air inside breaks down. But still a current flows through this conductor, through this circuit, through this arrangement. How does current flow through this arrangement? First question. The second question is, we already know what the Ampere's law is. V dotted with dl about a closed path equals mu naught times the current that is enclosed by that path. In other words, the current that pierces the area on which the path lies as an outer periphery. Now suppose that this distance d is really small, which also means that these plates are really close together. So if you fall away from the plates, it's as if this gap does not really exist. It just appears to be a continuous wire all straight through. Okay? So that's the philosophy of having a small d. It simplifies the argument, but by no means it's necessary. What's the magnetic field at point P, which is at some distance r from this current carrying conductor? What's the field here? The magnetic field. Sorry? Yes, the magnetic field at this point P is simply mu naught I over 2 pi r. Because for all practical purpose, this is an infinite current carrying conductor. Infinitely long. This gap is really small, it's imperceptibly small. So the field at all of these points can be calculated. Now how do you calculate this field? What do? Is I take a path, a closed loop around this current carrying conductor, and I move around this loop in a particular direction. And because of symmetry, the field is going to be the same along the circumference of this loop. And then I find the current that pierces this area. Which area am I talking about here? It's the area inside this loop. How much current goes through this green area? That's I. Multiplied with mu naught, you get V dot dl integral. Now I can, for the same loop, this loop is on the outer surface of some area. Now I can draw any area that I like. I don't have to draw a flat area. I can draw an area like this. Like a fishing net or a soap bubble. A soap bubble has a ring, and then the soap can go in any direction. The area of the soap can go in any direction. So this law just tells us the current that pierces an area. That current is simply mu naught J dotted with dA. This area is inside this closed path. But this area need not be a flat area. It could be any area whatsoever. Alright? आपको बात समझ आ रही है? आपके चेहरे पे कुछ संजीदगी है जिससे महसूस होता है कि बात समझ नहीं आई आगे ठीक है so I can draw any area that I like for the same path I can draw this area I can draw this area it's all the same and Ampere's law is still valid now consider a point here alright so one question another question a related question is that if my area well instead of being this flat area instead of being this curved tortuous area what if I use the same loop the same contour and the area that I'm talking about now is given here now this is also an area now how much current pierces this area nothing so would you get a different magnetic field here of course that's hilarious choosing a different area which is just a mathematical construct, the Ampere's law is a mathematical construct on blackboard, cannot give you a different line integral of the magnetic field. Because the magnetic field is given, you can put a Hall sensor here and measure the magnetic field. It's something that's real. A moving charge on this location will experience a force, you can measure it. So the forces and magnetic fields do not depend upon our wishes and desires. They are there, they physically exist. So choosing a different area evidently leads to a conundrum here. It leads to a puzzle here. The Ampere's law seems to give us incorrect results. You understand the question? Because if you've understood the question, you've understood half the answer. G. I can choose any area. If I have a path, this is my closed path. The area that I can choose can be flat. The area I can choose can be non-flat. I can have an area like this and I can find the current through this area. That will give me the line integral of the magnetic field around this loop. So what I've done here, I've chosen the same contour. I know that there exists a magnetic field which is given by this. So there is a magnetic field. Now if my area is given by this membrane and I've drawn it such that no current flows or pierces this membrane. There's no current flowing through the surfaces of this membrane. So evidently magnetic field's line integral about this path should be zero according to Ampere's law, but that's not the case. There's something missing here. What's the missing factor? Maxwell came in to rescue Ampere's law. And by a leap of imagination, he provided that missing factor. Alright? And how did he come up with an argument? Do you understand the question now? Umar? Sawal samajh aaya? Alright. We would like to preserve the sanctity of Ampere's law. We would like to uphold it. But there's something missing here. Okay. What the Ampere's law evidently tells us, the line integral of the magnetic field is equal to mu naught times the current that pierces an area. The area, you have the liberty to choose any area you like. You chose Gaussian surfaces at your desire. You chose Amperean paths at your desire that match the symmetry of the problem. But physics does not depend upon your desires. Okay? So you have to come up with a way to solve this apparent paradox. And Ampere's paradox was solved by Maxwell. Maxwell himself. So how do we solve this apparent paradox? Suppose I redraw this circuit. Now I'm just going to exaggerate the gap a little bit for clarity. Now suppose I take a point P. I take a point P here. Now I draw a circle which is coming out of the plane of the blackboard. Suppose this distance is R. This radius of the disc is capital R. Now I draw a circle of radius small r that comes out of the plane of black hole. It's a vertical circle. First question, will there be a magnetic field at point P? Physically, there's going to be a magnetic field. There is no reason why not. There is going to be a magnetic field. This gap is really small. For all practical purposes, it's an infinite current carrying conductor. So this field is going to be existent. It's going to be a non-zero field here. Alright? Now, how can I prove that? I just take this path and I draw an area that goes around like this. This is a point P dash at the same radius small r. So I've drawn a circle. My path is a circle. My closed loop is a circle. And this is the area that I'm talking about. Sorry. I have to be really careful here. Now, is there some current piercing this yellow membrane? Yes, that current is I. So about this path, there exists a magnetic field, and it has to be same at all radii because of symmetry. So that magnetic field B, P into 2 pi small r must equal mu naught times the current that pierces this area, which is I, function of time. So this is my magnetic field at these points P, even inside the gap. However, if I choose another area, suppose the area that I choose now is this flat area here. I have the same loop, the loop hasn't changed, the Amperian path hasn't changed, but now the area is flat and it's within the plates of the capacitor. Now what's the current through this area? Is there any flow of mobile charges through this area? Zero. So according to this area, the magnetic field 2 pi r turns out to be zero. But this is impossible. Two different areas are giving you different values of the magnetic field. This is totally, utterly impossible. So how did Maxwell resolve this paradox? What he observed was, it was a leap of his imagination. So there is a tinge of imagination and fanciful flights of your imagination. There is creativity in physics. It's not all about deduction. There's an inductive leap of faith as well when you create something new. And that's what Maxwell did. In this particular case, what you observe is that if a current I comes in, and it's a positively charged current because we talk about conventional current, this plate is going to get positively charged. And it's a conductor, so this charge is going to uniformly spread itself out. And because of polarization, this plate is going to get negatively charged. In other words, you can think in terms of feedback. There's positive charge coming in, but not going out. So this plate becomes positively charged. Here, there is current going out, because indeed there is a current flowing here, because you can put an ammeter and check it. There is current coming out, but it's coming out from nowhere. So there's a depletion of positive charge here, so this plate becomes negatively charged. So there's a buildup of charge, and hence a buildup of surface charge density here, sigma. And when this sigma builds up, it's a function of time, because the current is changing as a function of time. Because of this sigma, there's an electric field that is set up inside, in between the plates of the capacitor. So there's an electric field here. E. How much is that electric field? How much is that electric field? From the Precambrian times, that is before the midterm, you learned what this electric field is. This electric field is sigma over epsilon naught. Alright, now what's the electric flux through the blue area? Now I consider the blue area. I would like to find out the electric flux through this flat area. What's the flux through this electric flux? It's E dot dA. So the now this field is uniform. E is uniform. It's changing with time, but it's uniform. The field here is the same. It's only zero outside the plates. Okay? So this is E times this A. Let's suppose the area of the plates is capital A. Alright? Now this is sigma into capital A over epsilon naught. So this is the electric flux that pierces the blue area. That blue area lies inside this empyrean path. That's the blue area that we're talking about. Now this is the electric flux piercing the area. Let's find the derivative of this flux. The derivative of this flux is A is a constant, epsilon naught is a constant, derivative of the surface charge density. It's changing with time. But what's the surface charge density? It's charge per unit area. So this becomes I over epsilon naught. Because this is charge per unit area, Q over A goes away, the rate of change of charge that is built up on these plates is just equal to the current, because the current is bringing in the charge. Now what we observe here is something profound. Epsilon naught times the rate of change of flux through the area happens to equal mu naught I. So this object here has the same dimension as mu naught I. So this current is due to conduction. It is due to the transfer of mobile charge carriers. In this case, due to the motion of mobile electrons. But it's on equal footing to a changing electric flux through an area. Hence, Ampere's law can be modified in the following fashion. B dotted with dl around a closed path equals mu naught I. This is the traditional form of Ampere's law in which no electric fields are involved, no changing electric fields are involved, plus mu naught times. If I would like to have something that's analogous to I take epsilon naught times the rate of change of flux plus mu naught epsilon naught times the rate of change of electric flux through an area. This is the complete form of Ampere's law, and in honor of Maxwell, it's called Ampere-Maxwell's law. Ampere-Maxwell's law. This completes our set of Maxwell's equations. Let me write it in another form. B dotted with dl about the closed path equals mu naught times J dotted with dA this is I plus epsilon naught times the electric flux through that area, which is E dot dA and its time derivative. This is Ampere Maxwell's law. Just 2 minutes, I can't take questions, sorry. If I want to find a magnetic field here at point P, I can choose a path. Suppose my path is the circular path that I previously drawn. I want to find B dot dl about this path. Okay, it's a closed path. I can choose any area that I like. If I choose this area, then through this area there is no electric field that's changing with time. So this term goes to 0. Okay? There is only mu naught I that gives me the correct field. If I choose another area, if I choose this area, then there is no current, conduction current through this area. So this term goes to 0. I only have a changing electric field inside this region. And that changing electric field gives me something that is analogous to a current. A changing electric flux multiplied by epsilon naught is the same as the current that we're talking about, that passing through this conduction element. So a changing electric field also constitutes a current. It has units of amperes. This object is called the displacement current. So I can choose any area that I like. I'm always saved. There's nothing that's going to hurt me, because if I choose this area, the right hand side of the Ampere's Maxwell's law gives me a current, a conduction current. This term goes away. If I choose this area, this term goes away and I'm left with a changing electric field. So a changing electric flux is also tantamount or similar or akin, or it's at the same footing as a conduction current, and it's called a displacement current. What if, last point, last 2 minutes I promise. What if I have a situation like this? I'm at point S here, right? And I want to find the magnetic field at S. So my path is a circle of radius small r, and I would like to find the magnetic field at this radius. Now what if I choose an area which actually goes like this? I can choose an area like this. I'm at liberty to choose whatever area I like. Now it seems that it looks like an apparent paradox here, once again. Because the current that's coming in is I here. And then inside this region, there is a changing electric field as well. So there is a changing electric flux that pierces this region of the area. And there is also a current that's coming in. So do I get a bigger contribution on the right hand side of Ampere's law? Because in Ampere's law, this term is still the same. And then I'm getting an additional term due to the changing electric field. Because in this region, there is a changing electric flux that pierces this region. Is this an apparent paradox? It seems so, but it isn't, because this current that is coming in order for the charge to spread out, this current also goes like this. There's an I2 here and an I3 here, because charge must be delivered to these tips of the plate. So the total current, the conduction current that goes through this surface is not I, it's in fact I minus I2 minus I3. So this current has dropped a little bit, and it's dropped by just the right amount so that this electric flux that has gone up just matches the amount of flux that pierces this region. So everything is preserved and we are safe. There are no inconsistencies. All puzzles, all conundrums are solved, and I'd like to congratulate you because now we've gone through all 4 Maxwell's equations. Take a deep breath, go home, write down these equations from your memory. Don't look up a formula sheet. I don't believe in formula sheets. Write them down from your memory, because then you're going to tingle your memory, you're going to tingle your consciousness, and that will make you remember Maxwell's equations. Alright, see you today at 6:30 p.m. with the quiz. That's the 90 climax. Thanks.